Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video illustrates scaling operations for image transformations using basic OpenCV functions. This tutorial is the introductory step in processing images. The transformation methods are integral to computer graphics. These techniques use functions in OpenCV to accelerate the applications. There is some nominal background presented in the form of equations and code snippets. While our current focus is on 2D image transformations, the underlying concepts can be applied to 3D models. This basic introduction is necessary to ensure that we are all on the same page when we progress to slightly more advanced solutions using OpenCV, where these operations are applied implicitly. For those of you who are more advanced practitioners of computer graphics, please cut some slack for me so that I can get more viewers on the ride together. The basic image transformation methods are enumerated in the slide. Scaling, it's changing the dimensions of the image. Translation is moving the object from one position to another. Rotation, it's spin the image about a center point. Euclidean, a combination of scaling, translation, and rotation. Similarity, that's preserve shape and relative proportions. Affine is to maintain parallel lines as parallel. And finally, projective is to map lines to lines but not preserve parallelism. The focus for this tutorial will be limited to scaling. The two types of scaling are isotropic and anisotropic. Isotropic scaling enlarges or shrinks an object in all directions. In other words, the scaling is uniform in all dimensions. The same scale factor is applied to the object being scaled in all dimensions. This type of scaling preserves the object's shape. Imagine scaling a square shape. If the scaling is isotropic, then the shape will remain a square. The dimensions change proportionally in the applicable x and y for 2D shapes directions. Isotropic scaling will preserve the aspect ratio of the shape. Anisotropic scaling scales an object differently along its various axes. The scale factors being different in 2 or more dimensions. This type of scaling allows for independent scaling in each dimension. While the shape of the object changes, the angles between the lines remain the same. Imagine stretching a piece of clay unevenly, making it longer in one direction and shorter in the other. Anisotropic scaling does not preserve the aspect ratio. The principles of scaling are the same for 2D and 3D objects. However, in this tutorial on transformations, our focus is on 2D images. Isotropic scaling involves resizing an image uniformly in both the horizontal and vertical directions. This means the image maintains its aspect ratio while being enlarged or reduced. Specify a scaling factor. This is a number greater than 0. A value greater than 1 enlarges the image, while a value less than 1 shrinks it. Calculate new dimensions. Multiply the original image width and height by the scaling factor to determine the new dimensions. Resampling. This is the process of creating new pixel values for the resized image. Several interpolation methods can be used for this. Nearest neighbor assigns the pixel value of the nearest neighbor in the original image to the new pixel. Bilinear interpolation calculates the new pixel value based on a weighted average of the 4 nearest pixels in the original image. Bicubic interpolation uses a weighted average of 16 neighboring pixels for a smoother result. There are several other interpolation methods available, each with its own strengths and weaknesses. Isotropic scaling preserves the image's proportions. The choice of interpolation method significantly affects the image quality, especially when downscaling. For upscaling, bilinear and bicubic interpolation often produce better results than nearest neighbor. The initial point P is expressed as a column vector. The scale factors are the diagonal elements in the matrix S. For isotropic scaling, the scale factor is the same for all diagonal elements. The scaled point is calculated by multiplying the scaling matrix S with the initial point P. The scaling factor determines the amount of scaling. A value greater than 1 enlarges the object, while a value between 0 and 1 shrinks it. The scaling matrix is always a diagonal matrix with equal diagonal elements for isotropic scaling. S sub x is equal to S sub y is equal to S sub z. P prime is the column vector for the scaled point. It is calculated by multiplying the scaling matrix with the initial column vector for the initial point. In order to keep the presentation simple for now, I have omitted consideration of homogeneous coordinate system that is applicable for 3D objects. Here is the code snippet to illustrate the calculation of the scaled points in an image. The variable name image is a NumPy array that resulted from reading the input image file. Scale factor is the scaling factor applied to both coordinates of the points in the image. The new dimensions of the scaled image are obtained by multiplying the original dimensions of the scale factor. Then we iterate over each point in the new image and obtain its value from the original value multiplied by the scale factor. To keep the calculations and input parameters simple for demonstration purposes, a linear interpolation is used. In practice, this code snippet will be superseded by the OpenCV resize function, where a large number of interpolations are available for use during the scaling calculations. The key function in OpenCV to perform scaling is resize. In addition to performing either isotropic or anisotropic scaling, the function offers flexibility in controlling the output image size and the interpolation method. The parameters are src for the input image, dsize for the desired size of the output image as a tuple, width and height. This is optional. Fx, scale factor along the horizontal axis. This is optional. Fy, scale factor along the vertical axis. This is optional. Interpolation, the interpolation method used is specified as inter underbar nearest, which is the nearest neighbor interpolation, inter underbar linear, bilinear interpolation, which is the default, inter underbar area, area-based interpolation, inter underbar cubic, bicubic interpolation. You can either specify dsize or f and fy. If both are provided, dsize takes precedence. You should specify the interpolation method based on your requirements for image content and desired output quality. Either dsize or both fx and fy must be non-zero. Anisotropic scaling is a transformation that modifies the dimensions of an object by different factors along different axes. Unlike isotropic scaling, which uniformly scales an object in all directions, anisotropic scaling allows for independent scaling in each direction of the coordinate axes. Anisotropic scaling is non-uniform scaling. The object's dimensions are changed disproportionately. The aspect ratio changes. The shape of the object is altered due to different scaling factors. Independent axis scaling. Each axis can be scaled independently. Stretching or compression. Depending on the scaling factors, the object can be stretched or compressed along specific axes. Preservation of shape. While the overall shape changes, the relative proportions within the object are maintained. Matrix representation. Anisotropic scaling can be represented by a diagonal matrix with different scaling factors on the diagonal. Applications: widely used in image processing, computer graphics, and geometry for various transformations and effects. While anisotropic scaling can preserve the overall shape of an object, it can distort angles and distances. When applying anisotropic scaling to images or 3D models, appropriate interpolation techniques are essential to avoid artifacts. In anisotropic scaling, The points scale differently along each axis since the scale factor is different for each axis. The scaling matrix is always diagonal for an isotropic scaling. The diagonal elements represent the scaling factor for each axis. Matrix multiplication is used to apply the scaling transformation to points or vectors. By multiplying the scaling matrix with a point's coordinate vector, the point is scaled differently along each axis. The code snippet is similar to that for the isotropic scaling, except for two variations. First, the scale factors in x and y dimensions have their respective values. This is the key distinguishing calculation for anisotropic scaling. Second, in order to make the solution more portable, I'm ensuring that the conversion works on all channels in the image. Again, we will run this code shortly to demonstrate the concept, but in practice you are encouraged to use the resize function in OpenCV where possible. The key function in OpenCV to perform scaling is resize. Anisotropic scaling is performed by using different values for fx and fy. Naturally, with different values for fx and fy, the aspect ratio of the image will change. This scaling will distort the resulting image. Choosing the right interpolation method is crucial for maintaining image quality. For our introductory purposes, in limiting our discussion to scaling along axes, we have deliberately omitted anisotropic scaling in arbitrary directions that can be performed with more complex transformation matrices. One should choose the interpolation method to resize images based on the desired image quality and specific application needs. The available methods are nearest. This is the simplest method. It assigns the value of the nearest pixel in the original image to the new pixel. It often results in a pixelated appearance, especially when upscaling. Next, we have linear. The calculation method is known as bilinear interpolation. It considers the 4 nearest neighbors to compute the new pixel value. It generally produces better results than nearest neighbor, especially for upscaling. Next, we have area. This method resamples using pixel area relation. It is best for downsampling as it preserves image information better than other methods. It is impractical for upsampling. Next, we have cubic. This method uses bicubic interpolation over a 4x4 pixel neighborhood. It produces smoother results than bilinear, but is computationally more expensive. It is a good choice when having to deal with upscaling and downscaling. Finally, we have Lanczos. This method performs Lanczos interpolation over an 8x8 pixel neighborhood. It provides high-quality results, but is computationally intensive. It is a good choice for upscaling. For upscaling, linear, cubic, or Lanczos are generally considered better for image quality purposes. For downscaling, area is often the best choice to preserve image information. For speed, nearest is the fastest, followed by linear, cubic, and Lanczos. Let us examine each interpolation method separately in the next slides. Nearest neighbor interpolation is the simplest method for resizing images. It involves directly assigning the pixel value from the original image to the corresponding pixel in the resized image. The calculation steps are: determine the scaling factor, calculate the ratio of the new image size to the original image size, calculate new pixel coordinates. For each pixel in the new image, determine its corresponding coordinates in the original image using the scaling factor. Round to nearest integer. Round the calculated coordinates to the nearest integer to get the pixel location in the original image. Assign pixel value. Assign the pixel value from the original image at the rounded coordinates to the corresponding pixel in the new image. It is popular for downsampling owing to its simplicity. In this example, the original image, for the purposes to understand the calculation process, is a 2 by 2 image. In the real world, we will not deal with 2 by 2 images commonly. We will scale the original image by a factor of 2 in both dimensions. The resized image will be a 4 by 4 matrix. Each pixel takes the value of its nearest neighbor in the original image using the formula shown in the middle column of the table on the slide. Nearest neighbor interpolation is computationally efficient. It can introduce unexpected values when enlarging resized images if the pixel values change abruptly. It is better for downscaling images owing to its simplicity and preservation of original pixel values. While nearest neighbor interpolation is straightforward, it is often not preferred for image resizing owing to the potential for image quality degradation. Bilinear interpolation is a method that estimates the value of a function at any point within the rectangle defined by 4 known values at the corners. In the context of images, it is used to determine the pixel value at a non-grid point based on the values of the 4 nearest pixels in the original image. The processing steps are: identify the 4 nearest pixels. For a given pixel location in the resized image, determine the 4 closest pixels in the original image. Calculate weights. Determine the relative distances of the target pixel to each of the 4 corner pixels. These distances will be used as weights for the interpolation. Interpolate along rows. Perform linear interpolation between the top 2 pixels and the bottom 2 pixels. Interpolate along columns. Perform linear interpolation between the 2 interpolated values from the previous step. Some of the implementation considerations are: efficiency. For large images, optimizing the interpolation process is crucial. There are techniques like pre-calculating weights or using hookup tables that can improve performance. Boundary conditions. Special handling is required for pixels near the image edges. Image quality. While bilinear interpolation is generally better than nearest neighbor, be prepared for blurriness when upscaling with large scaling factors. By understanding the underlying mathematical principles and implementation details, you can effectively apply bilinear interpolation to resize images in various applications. The conversion formula for linear interpolation is shown in the middle column of the table in the slide. The original image is 2 by 2 matrix to keep the example simple. In the resized column, we add the left and right numbers from the original set and divide by 2. We get 15 and 35 respectively in the middle column. In the second operation, we add the numbers in the top and bottom rows and divide by 2 to obtain 20, 25, and 30 in the middle row. Linear interpolation is computationally efficient. However, it can introduce unexpected values when enlarging resized images if the pixel values change abruptly. It is better for downscaling images owing to its simplicity and preservation of original pixel values. While linear interpolation is generally better than nearest neighbor, it can still produce some blurriness, especially for large scaling factors. Area interpolation is a method for downsampling images that preserves the total pixel value within a region. It is particularly useful for reducing image size while maintaining overall image intensity. The calculation steps are: divide the original image into rectangular blocks. The size of the blocks corresponds to the downsampling factor. Calculate the average pixel value. For each block, calculate the average of all pixel values within it. Assign the average pixel value to the corresponding pixel in the downsampled image. Each block in the original image maps to a single pixel in the downsampled image. The average pixel value within a block may be expressed as average pixel value is equal to the sum of pixel values in the block divided by the number of pixels in the block. Area interpolation is generally used for downsampling and not upsampling. For upsampling, methods like linear or cubic interpolation are more suitable. Area interpolation is often used in image processing tasks where preserving the overall image intensity is more important than preserving fine details. The process: divide the original image into rectangular blocks. The size of these blocks corresponds to the downsampling factor. For example, to downscale an image by a factor of 2, divide the image into 2 by 2 blocks. Calculate the average pixel value. For each block, compute the average of all pixel values within it. Assign the average value to the corresponding pixel in the downsampled image. Each block in the original image maps to a single pixel in the downsampled image. Consider the original image illustrated by pixel values on the slide. To downscale it to a 2x2 image using area interpolation, divide the image into 4 2x2 blocks. Calculate the average of each block. Top left block is 1 plus 2 plus 5 plus 6, the whole divided by 4 is equal to 3.5. Top right block is sum of 3 plus 4 plus 7 plus 8, the whole divided by 4, which is 5.5. Bottom left block is the sum of 9 plus 10 plus 13 plus 14, the whole divided by 4 is equal to 9. Bottom right block, the sum of 11 plus 12 plus 15 plus 16, this divided by 4 is equal to 11. The downscaled image is shown in the right column under the header resized. Cubic interpolation involves fitting a piecewise cubic polynomial to a set of data points. Each polynomial segment is defined over an interval between two data points. The key to cubic interpolation is ensuring smoothness and continuity of the curve and its derivatives at the data points. Bicubic interpolation is an extension of the bilinear interpolation, considering a 4x4 neighborhood of pixels instead of just the 2x2 neighborhood used in bilinear interpolation. This provides a smoother and more accurate interpolation, especially for image upscaling. Bicubic interpolation is computationally more expensive than bilinear interpolation, owing to the large number of calculations involved. Special handling is required for pixels near the image edges. Careful implementation is necessary to minimize artifacts like ringing or overshoot. Bicubic interpolation generally produces smoother and more accurate results compared to bilinear interpolation, especially for upscaling. It can better preserve fine details in the image. The steps described on this slide are very simple and basic. The actual implementation involves complex matrix operations and boundary conditions. The key steps are: identify the 4x4 neighborhood. For each pixel in the target image, determine the corresponding 16 pixels in the source image. Set up the system of equations. Based on the 16 pixel values, create a system of 16 linear equations. The unknowns in these equations are the coefficients of the bicubic polynomial. Solve the system of equations. Solve the system of equations to obtain the 16 coefficients. Evaluate the polynomial. Use the calculated coefficients to evaluate the bicubic polynomial at the desired subpixel location within the 4x4 block to obtain the interpolated pixel value. The computational challenges are matrix inversion. solving the system of linear equations involves matrix inversion, which can be computationally expensive. Boundary conditions. Handling pixels near the image edges requires special care. Numerical stability. The interpolation process can be sensitive to numerical errors. Lanchas interpolation is preferred over simpler methods like bilinear or bicubic interpolation when computational resources permit. There are three considerations for the calculations: kernel, convolution, and summation. The kernel. The core of the Lanchas interpolation is a mathematical function called the Lanchas kernel. This function is a sinc function, sin x over x, multiplied by a windowing function. The windowing function is typically another sinc function truncated to a specific number of lobes. Convolution. For each pixel in the target image, a Lanchas kernel is centered at that point. The kernel is then multiplied with the corresponding pixels in the original image. Summation. The products from the convolution step are summed up to produce the interpolated pixel value. The Lanchas interpolation uses a larger neighborhood of pixels compared to other methods, leading to better results. The Lanchas kernel has a smooth and oscillatory state which helps to reduce artifacts. However, the more complex calculations, it is computationally more expensive. The Lanchas interpolation is a more refined approach to estimating pixel values, providing a balance between image quality and computational efficiency. It is very effective during upscaling operations because it preserves details. In Lanchas interpolation, the sinc function serves as the basis for the interpolation kernel. By multiplying the sinc function with a window function, we create a more localized and computationally efficient kernel. This kernel is then used to weigh the neighboring pixel values when calculating the interpolated pixel value. By multiplying the sinc function by another sinc function, we create a windowed version of the sinc function, which is more localized and computationally efficient. The Lanchas kernel provides a good balance between sharpness and smoothness in the interpolated image. The three considerations for the calculations are kernel, convolution, and summation. The kernel. The core of the Lanchas interpolation is a mathematical function called the Lanchas kernel. This function is a sinc function, sin x over x multiplied by a windowing function. The windowing function, as shown on the slide, is typically another sinc function truncated to a specific number of lobes. Convolution. For each pixel in the target image, a Lanchas kernel is centered at that point. The kernel is then multiplied with the corresponding pixels in the original image. Summation. The products from the convolution step are summed up to produce the interpolated pixel value. The choice of interpolation method significantly impacts the quality of the resized image. Here is a comparison of the common methods. Nearest neighbor interpolation. The pros are simple, fast, and preserves original pixel values. Cons are introduces noticeable artifacts, especially when upscaling. The next method is bilinear interpolation. The pros are better quality than nearest neighbor, especially for upscaling. The cons are can introduce blurriness, especially for large scaling factors. The next method is bicubic interpolation. The pros are produces smoother results than bilinear, handles edges better. The cons are more computationally expensive and can introduce ringing artifacts. The next method is area interpolation. The pros are preserves average pixel intensity, used for downsampling. The cons are introduces blurring and it's not suitable for upscaling. Finally, the last method is the Lanchos interpolation. The pros are excellent image quality, especially for upscaling. The cons are computationally expensive. The key trade-offs that you should consider are speed versus quality. Nearest neighbor is the fastest but produces the lowest quality, while Lanchos is the slowest but often produces the highest quality. Preservation of details. Nearest neighbor preserves original pixel values but can introduce artifacts, while the other methods might introduce blurriness. Computational cost. Methods like bicubic and Lanchos are computationally more expensive than nearest neighbor and bilinear. Finally, image content. The choice of interpolation method can also depend on the type of image being processed. For example, images with sharp edges might benefit from bicubic interpolation, while images with smooth gradients may be better suited for bilinear interpolation. The demonstrations of scaling images will be limited to the following basic methods of interpolation: nearest, linear, cubic, area, and Lanchos. We will limit ourselves to isotropic scaling because anisotropic scaling will introduce another parameter to contend with, and it may have an effect on our basic interpretation of a specific interpolation method. We will demonstrate the interpolation methods without relying on OpenCV for the first example. Then we will resume the demonstrations using OpenCV for all applicable interpolation methods. Our primary focus will rely on Python scripts. We will also demonstrate the equivalent operations using C++ also. I will provide examples in Java in future tutorials when I resume work on demonstrating OpenCV applications under Android Studio. While this slide illustrates the results of displaying the images without using OpenCV for interpolation, there are two fundamental flaws in my demonstration. I upscaled the original image and performed the interpolation. Then, for presentation purposes, I had to render the image to fit the presentation size and position. Naturally, this operation resizes the images back to its original dimensions. Also, there is further implicit resizing when these images are rendered in the YouTube viewing window. You can only get a feel for the interpolation results when you view the results in an unmodified window. Let us use OpenCV to illustrate each interpolation separately for the next demonstration. Again, viewing the images on the screen will not give you an understanding of the variations from the choice of the interpolation method for the resized image. We will shortly demonstrate the interpolation methods with these images too. So let's look at the various interpolation methods for scaling using the OpenCV function called resize. So here we have resize, and here are the parameters for the call. So we specify the source image. The destination image is optional because it will be assigned to a variable. And then we have the fx and fy in isotropic scaling. They're equal. And for this demonstration, we're going to use a value of 3.0. So in the scaling function, we read in the image file from the source command line. And then after reading that, we make sure that it has some data in it. If it's not none, we will just post a message and exit. Then we retrieve the scale factors and immediately call resize. So this is the variable where the image was read, and we specify 3.0 and 3.0 for this. And for the first demonstration, we'll use nearest for the interpolation method. And then after that's done, we go ahead and show the original image using the IAMShow command, and then we show the demo image that we had, which we call image scaled in here, right? So let's go ahead and run this, and I'll just right click on the tab and click on run. So the script produces two windows through the IAMShow command. The first window is the original image, and the second window is the scaled image by a factor of 3. It's an isotropic scaling, so it's equal in x and y, and it's using the nearest neighbor interpolation. So here we have the original image, and we are going to see the scaled image using nearest neighbor interpolation with a scaling factor of 3.0. Here is the scaled image with a scale factor of 3 using nearest interpolation. Unfortunately, on the screen, it's not very easy to see, and the ideal way to experience this is to run the exercise yourself and get a feel for it. But you can clearly see at the edges, it's very pixelated. Similarly, at the center, I can clearly see that it's pixelated. As we go along the radial directions, there is slight differences between the original and the scaled image, but it's very hard to see without numerical values. But clearly, this is not a very good scaling using nearest. So we'll look at some of the other methods and see if we can do better. Let us now use linear interpolation for the scaling. Linear, by the way, is default. And we can go ahead and type that in. And everything else remains the same. The scale factor is still 3.0, and the source file is still the color wheel. So the scaled image will be called image scaled, and the file that we've read is image read, and we're going to display both of them in their own individual windows. So once again, let's go ahead and run this. Right click on the tab and then click on run. So once again, we get two windows from the two I am show commands. The window on the left is the original image, and the window on the right, which is slightly larger by a scale factor of 3, is using linear interpolation with a scale factor of 3.0. So we will go through the larger window in a little more detail now. So we can see with the linear interpolation using a scale factor of 3.0, the edges are still a little bit rough, but there is a noticeable improvement in the center here because of the way the interpolation is done with extended linear values. And so this is slightly better than the previous case of the nearest neighbor. It's an improvement when we're doing upscaling. The next example is to use area interpolation for the scaling. We keep the scale factor still at 3.0 for x and y and just change the interpolation method to enter underbar area. And then, of course, we will display the original image and the scaled image in separate windows. Here are the two windows from the two I am show commands again. The left is still the original, and on the right we have area interpolation using a scale factor of 3.0. As we have remarked in our presentation, using area scaling for upsizing is not really a very good idea, and this is clearly evident by the pixelation at the center of the image here. On the edges also we still have some problems, so perhaps I should have chosen a different scale factor for area, and let me do that by using a scale factor of 0.5. And now you can see that the resulting image, by scaling it by 0.5, which is reducing it by half, the window has become smaller than the original image. This is to be expected, but clearly the quality of the image is much better now. So we're using area interpolation with a scale factor of 0.5, and you can see there is a definite improvement in the center of the screen from the previous image, as well as at the edges around the perimeter, the boundaries. So clearly area interpolation works best when you're downscaling. Let us now repeat the exercise by using cubic interpolation for the scaling. We will leave the scale factors at 3 to be consistent with our previous demonstrations, and we will show the original image that we read in, and then we'll show the scaled image. So the command for the CV resize in shown statement here, let's go ahead and run it by clicking on the tab and selecting run. So I'll skip showing the original image and just focus on the cubic interpolation with the scaling factor of 3. There is a significant amount of artificial artifacts, as they call it, ringing or other kinds of distortion that cubic has introduced around the boundaries. And this is to be expected because of the challenges in interpolating with a cubic polynomial around a boundary. And this is consistent around the entire perimeter. Similarly, in the center, we can see this is not as smooth as we would like, as in the case of the linear extrapolation. And again, it's a consequence of cubic interpolation. So although cubic interpolation has its place and may be preferred, its computational work introduces some additional artifacts that may be undesirable for certain images. The final method in this series of interpolation is the Lanchos method. And in the case of OpenCV, to specify that, we use inter underbar Lanchos 4 to designate the interpolation method to be Lanchos. So we'll make that change here, and we'll stay with the same scale factors, 3.0 for x and y, and then display again the original as well as the scaled image, and we will go ahead and run the code now by right-clicking on the tab and clicking on Run. Again, I'm omitting the display of the original image window because you've seen it several times now, and just jump ahead to the Lanchos window, which has been scaled by a factor of 3. As you can see on the image here, it's a little better at the center, but at the edges also it's quite refined, but I can still see many artifacts. So the jury is still out on what would be the best interpolation method for this color wheel. But I hope you get the idea that we need to try different methods for different situations, and the results will vary based on the original image. So let's go ahead and now try out a portrait, but instead of using Python, I'm going to use C++ to demonstrate the same code. Let us now work with another image to demonstrate scaling. And in this instance, we will use C++ as the programming language to interface with OpenCV. So while there are many IDEs that one could use, I've chosen Kdevelop, and this is version number 5.6.1. You can use any other IDE if you like. Qt, spelled KT, is another good one to use. And of course, you can use command line, you can use make, you can use CMake. So even Genie, that is very popular on Raspberry Pi, should work for you. The most important file, apart from the source code, of course, is the CMake list.txt. So if you can see here, this is a minimal version that has been adapted from the OpenCV tutorials to run this demonstration. And the file requires a header with the minimum version, generally around 3.5 and better. Obviously, it's a good idea to give the project a name that you can reference in the rest of the file. And then the most important one here is for the directive find package, and go ahead and locate the OpenCV package. Similarly, for our compilation of the source for the header files, it is important to include the directories and get access to them for our compilation. We also want to include some of the source files, not all of them. Of course, here we have only one, so we assign that to that project. And finally, when we're linking the library to create the executable, we wanted to go ahead and locate the OpenCV libraries and include them. So as you can see, this CMake list.txt makes life very easy and very flexible for your development work. So use the one that is provided by OpenCV and modify it as we have it in this example in here. Now let's go back to the source code here, and it's again adapted from the OpenCV tutorials, and we're going to be doing scaling using nearest neighbor, and for scaling we'll use the OpenCV function resize. So the first thing we do is to make sure that we've included the OpenCV headers, and it's here. And if this doesn't work, then you better go fix it in your CMake list or check your installation of OpenCV. And then for convenience in cutting down the amount of keystrokes or text in the file, we just use standard prefixes so that it can go ahead and use these namespaces. And the file name is provided through the command line. Let's not worry too much about it right now. We'll get into it, but we can see that what we do is we have an image original that we call as the source file name that we are going to be converting to from the input file. So the image file is image file. We read it. We don't modify the color codes or whatever channels they have. And then if we assert the conditions to make sure that it does contain data, and we then display it in a small window. The next thing we'll do is scale it, given the scale factors, and in order to be consistent, I've kept it at 3.0. And we go ahead and use the OpenCV function resize, and we apply the scale factors, and here is the interpolation. So that's all we're going to do, just in keeping with the previous Python program. We're going to display the original window, and then we'll display the resized window, and the window title bar will contain the type of scaling that is performed and the scale factor. To compile the source code, we click on the project name in here, and on the drop down we select build. As you can see in the window here, it completes successfully. Once the build is complete, we can go ahead to the menu bar, and there are other ways of doing it also, and we can click on execute. There is an indefinite wait key, so we need to go ahead and click on enter so that the scaled image will be displayed. And here it is. So you can see side by side the original image and the scaled image. And clearly the pixelation shows up more clearly than I could do in the original presentation slides. The original window is now displayed on the screen. The pixelation is very clearly prominent in the areas that I'm using my arrow to point to. And it differs from the original image, and you can put it side by side and it should become apparent. The other place where the pixelation is very clear is in the collar area. So this white area here, when we do nearest, really doesn't do justice even at a scale factor of 3. So once you run these kinds of experiments with the different interpolation with your portrait image or any other image that you have, you can draw your own conclusions as to which interpolation works best for which image. Let us now run the scaling with linear interpolation. So in the resize command, I've specified inter_bar linear to select the linear interpolation, and I've also accordingly modified the header of the window that will show the linear interpolated image. So let's run this. At first glance, the linear interpolation looks slightly better than the nearest. I mean, the collars are not that pixelated, the nose area is not that pixelated, and the forehead area here too is not that pixelated compared to nearest. So in terms of this specific portrait, linear seems to be slightly better than nearest, although not as good as we would like it to be. The next interpolation is by area, and so we pass that as a parameter to the resize statement in here. And we also make corresponding changes to the window title so that when we capture that image and save it, we will have a record of what was going on. So let's go ahead and run this and see the results. As you can see from this image, perhaps not so clearly on the video, but perhaps when you do the experiment yourself, you will see that area really doesn't work very well for upscaling. This is almost as bad as nearest, not as good as linear, which in itself was not really very good. But still, nevertheless, you can see why we say that area should never be used for upscaling. Our next interpolation method is cubic. And so we let resize know that we're going to be using cubic, and for I am show, we want to make sure that the window header title also states cubic. And we'll go ahead and run this to see the results of the scaling. While the results of cubic interpolation for scaling with a factor of 3.0 looks reasonably good, there are some clear signs of artificial artifacts being introduced known as ringing that is commonly associated with cubic interpolation. Obviously, we don't have to contend with the boundary conditions for the images, but ringing seems to be clearly apparent when there is an abrupt change in the transition from dark to lighter areas and vice versa. So again, we have to be careful on how we decide to use cubic interpolation for scaling. Finally, for the last interpolation method, we will use Lanchos. So again, we specify inter_Lanchos 4 as the parameter for resizing it, and then to the command there. And obviously, we need, as cosmetic, we need to change the title in the window for record-keeping purposes. So no further changes are required, just like in all the other cases. And so let's go ahead and execute this. So Lanchos seems to have done a much better job in reducing the pixelation around the forehead and the nose, as well as the collar. But it still does have some issues with the transitions when there is a distinct boundary between the dark areas and the light areas. So while it's better than the other methods, clearly it's not absolutely optimal. So again, as I've remarked before, you have to try out all interpolation methods available to you with your image and then satisfy yourself as to which one meets your needs and the target purpose. As promised earlier, I'd just like to quickly show you how I pass parameters through the command line when developing with kdevelop. So here is the file that I go through, which is run and then launch configurations. And in launch configuration, there's an argument where you can specify your command line parameters. So let's look at the command line parameters. I don't want to go through everything. I think if you're using kdevelop, you should have known by now how to do it, or other systems have other methods. But essentially, there is a field here called arguments, and you type in the first parameter, which is in our command line is the name of the file that we want to read in. So as simple as that, and then in the source code, we're able to read it. So in the source code, we use the classic argument count and argument vector to all the argument variables. And the first one, as I showed you in there, is the name of the image file. And then we just assign that to a local string variable and read it in an unchained format. It's just as simple as that. It's just convenience for my sake. You could have your own way of doing things, and perhaps you can get to explore argument passing along the way. So I hope that these sets of exercises have been useful for you in demonstrating how to use scaling with the different interpolation options, and I've demonstrated it using Python and C++. Obviously, my whole concept behind this is to ask you to use OpenCV, but at the same time give you some background as to the math beneath the covers, but not as much detail that you would be writing your own versions of these interpolations. In other words, I don't want you to reinvent the wheel. I'd rather you be productive using OpenCV. Before I conclude this tutorial, I'd like to go over another example of anisotropic scaling, but with a slight twist. I will not display the images, but instead write it to a file, and in the process show you how to use the OpenCV IamWrite command to write the image to the file, as well as place some text on the image before writing it to the file. So again, slightly same variation. We will do the scaling with CV resize, but we will have two different scale factors, one for fx and one for fy. And I'll just go down here and show you what those values are. So in the case of fx, in x direction, we will stretch it 3 times. And in the y axis, we will do it only 1.5 times. The image is here referenced, and you can see it in the window in here. This is the original image that we're going to scale anisotropically. Now, the twist comes in the code in the form of I will do all these interpolation operations in one loop. So do nearest, linear, area, cubic, and Lanchos, as we have done in the case of the isometric scaling. So to write text, we need to have a string buffer. Initially, of course, I just call it default. Doesn't matter what you have, can have a null string there. And then choose a font. And in this case, I've chosen the most common font that we use in OpenCV. There is a font scale that is required, a thickness, and in terms of the value, remember it's BGR, so it's red and green, 25, 255, 255, which means it's basically yellow. And we would then go ahead and assemble the text in here. So we would get the text as the interpolation type. And if you're not familiar with Python notation for all this, perhaps we can get into it later on. So basically, I'm getting the suffix list, the name of that, which matches the index, so linear to linear. So the same sequence as the top there. I get that, and then I have the scale factors also written out as a string. And then place the text size, get the text size from the CV function, get text size, get the text width and height, and make sure it's about 10 pixels above the bottom. And then we place the text in the image before we write it. So very straightforward, in terms of execution, it should run very quickly. And so let's go ahead and run this. I'll click on the right tab, and notice that it just says Amaryllis2. In a minute, when I run it, you'll see the names of all the other files that it's written to the folder. So go ahead and run. And it's run immediately, and you can see that it's written a file called area, it's written a file called Lanchos, linear, and so on. So I'll just pull up nearest for the sake of discussion and show you that it's stretched it 3 times in X and 1.5 times in Y. And here is the text string that we assembled and we've written down. So in the overlapping files that I will show in the subsequent video, you will see all the files that are shown as images here. So I hope this is a useful demonstration for you in terms of anisotropic, as well as how to place text into an image and how to write the image. And there, of course, there are some options that I have eliminated here that I have not used. But while you're writing the images, you can do a couple of other things also. And perhaps in later tutorials, when we get more into OpenCV, we'll see what those parameters are. This video tutorial demonstrated the basic image transformation techniques directly supported by OpenCV for scaling. Future tutorials will examine other image transformation techniques using basic OpenCV functions. Understanding these techniques, especially for those who have no prior computer graphics experience, will facilitate the upwards migration to more advanced techniques in image processing. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You are always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance from OpenCV for many examples on basic concepts and from the free open source software, FOSS, for the 3 integrated development environments: IDE from PyCharm for Python plus more, from KDevelop for C++, and Google for Android Studio. Also, the backbone for the presentation of this video is from Inkscape, OBS Studio, Kdenlive, LibreOffice, and of course, Ubuntu. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to you all for the assistance.